Welcome to the class. Today we will talk about Word2vec. This is a very important dimensionality reduction algorithm. Word2vec, as the name suggests, is to convert words into vectors. It comes from natural language processing, NLP. So let's review the process of NLP. Here is an example. Here is a text containing a sentence. The sentence is, the cat sat on the mat. First, we need to do standardization. Okay, so the standardized text is to remove the period and also make all the letters lowercase. Then we need to do the tokenization. We split the sentence into words. So there are a lot of words, or you can call them tokens. Then we do the indexing to make the token index convert each word into a number. And finally, we do one-hot encoding, or you can call it embedding. So we convert all the tokens into a one-hot encoding index. This is the typical flow of natural language processing. Word2vec do one step further to compress the one-hot encoding vectors into dense vectors. In other words, Word2vec reduce the dimension of one-hot encoding vectors. It do the dimensionality reduction. Word2vec is one algorithm for word embeddings. Embedding means dimensionality reduction, to embed the vector into smaller vector space. This is embedding. So why do we need embedding? And embedding is especially important for text. Why? This is because unlike other data like audio or images, both audio and image data are dense vectors. Right? The vector include the image pixels or the audio spectrum. On the other hand, the vector for text are sparse. Remember, we convert word into one-hot encoding vectors, which means all the data in the vector are 0 except 1. So the text data, for example, a sentence, may consist of multiple data, not 0, but most data in the text are 0. Remember the famous phenomena in machine learning, curse of dimensionality. If we have a huge sparse data, it will be very difficult to train a good model for the input data. So that's why we need word embedding for text. Word2vec was proposed for word embedding. It embeds one-hot encoded word vectors into dense vectors. It was first proposed by Mikolov, Thomas, in 2013. And it was so successful, and it becomes one of the most important dimensionality reduction algorithms. It has been go beyond embed one-hot encoding vectors. You can see many applications today. We can say that Word2vec is one of the most important dimensionality reduction algorithms. Back to natural language processing. There are two types of NLP model. One is bag of words, and another one is sequence model. For example, look at this sentence. The quick brown fox jumped over the lazy dog. For bag of words, it does not account for the order of the words, so it looks like a bag that includes a lot of words, but we do not care about the order of words. On the other hand, The sequence model will consider the input order of the word. So the word will input into the model one by one. The quick brown fox jump over the lazy dog. Sequence model consider the temporal relationship between words. So it consider more advanced, but backup words are still very effective. Word2vec is one kind of backup words model. There are two kinds of methods for backup words models. The first is the count-based methods. It considers how often some word co-occurs with its neighbor words. The most famous count-based method is latent semantic analysis. Word2vec belongs to second category of backup words model. It's called predictive methods. It predicts a word from its neighbors. It's a bit like the crossword puzzle that you need to fill the missing character in a word. So we will use a word to predict its neighbors. But in this case, we need to predict the missing word in a sentence. Okay, so again, there are two main different predictive methods. One is continuous backup word models, and the second is skip-grade model. Continuous backup words and the skip-grade are both predictive models. Let's look at the continuous backup word. This is the continuous backup word method. Continuous backup word use the neighbor words before or after the target. This is my target. So we can use the neighbors before. In this case, we use two words before our target word and two words after our target word to predict the target word. On the other hand, the skip-grade use the one word and predict its neighbors. So we have only one input, one word in a sentence. Then we want to predict its neighbors using the single word. So this is called the skip-grade model. Here is an example of a skip-grade model. The skip-grade model can also set the window size. Suppose we set the window size to 2. Let's see the example sentence. The first input is so the skip-grade model will generate a training sample like the quick, the brown. Usually we will remove the too frequent or too common words like the. Okay, so if we move the window, then we will use quick to generate training examples. So suppose the input is quick, then we will generate the quick brown, quick fox. Then suppose the input word is brown, then we will generate a training example like brown quick, brown or brown fox or brown jumps. Okay, so you can see the examples here, like the brown quick, brown fox, brown jumps. So this is how the skip-grade model generates training examples. Let's see how to use the skip-grade model to create Word2vec. By the way, most material and the pictures in this class are from Chris' website. You can visit his blog, Google the Word2vec tutorial, and you will find his blog. Here is the architecture of Word2vec. In fact, the Word2vec model includes only one hidden layer, one hidden neuron, and the input is the one hard encoded vector of one word. Remember, we want to use one word to predict the neighbors This is the skip-grade model. So the input is the one-hot encoding vector of the word. And then we want to output the probabilities of other words that is in the neighborhood of the input. So the output is actually a softmax classifier. Let me redraw the architecture. So it should look like this. There are two one-hot encoding vectors with a much smaller hidden layer in the middle. Also, it's densely connected. So actually, the smaller embedded vectors are the hidden layers. Let's go into more details in the following pages. Let's apply neural network for skip-grade model. So the input vector is a one-hot encoded vector. Suppose this vector represents the word fox. This station is 1 means that this vector represents fox. Then the input will go through one hidden layer in the neural network. So Word2vec is actually not a deep learning model, but it's a neural network. It only have one hidden layer, so it's not very deep. Okay, so the output is the softmax classifier because we want to output the probability of each word that is the neighbor of fox. So suppose here are some examples. We can output the probability of brown or jumps or quick. The probability of brown jumps quick should be very high or higher than other words because in our training example, the quick brown fox jumps over the lazy dog. Those three words are in the neighborhood of fox. But where are our embedded vectors? Remember, Word2vec is trying to convert the sparse dense one-hot encoding vectors into dense embedded vectors. So where are the vectors? In fact, the vectors are the weight matrix of the hidden layer. Okay, in our previous example, we have used 10,000 vocabulary. Also, our one-hot encoding vector is 10,000 dimension. And suppose we choose 300 neurons for the hidden layers, then we will have 10,000 by 300 weight matrix. And this matrix is, in fact, the word vector lookup table. Each row vector represents the embedded vector for the corresponding word. So now we have 10,000 embedded vectors, and because we have 10,000 vocabulary. Each row vector represents the new embedded vector for the corresponding word. Why can we use the row vector as embedded vector directly? Here is the explanation. We can use the hidden layer as the lookup table for our words because if you multiply one hot vector, here's a one hot vector, then it's actually equals selecting the matrix row corresponding to the data entry, right? So if you multiply, suppose we have 5 words, if you multiply the one hot vector with our hidden layer matrix, it's like select the 4th row vector, right, from the hidden layer weight matrix. So we can use hidden layer as the lookup table. And by training the neural network for the skip-grade model, we can have embedded Word2vec lookup table. Another key point is that the number of neurons in the middle, in the hidden layer, is corresponding to the dimension of your embedded vector, right? So suppose we have this matrix. This matrix means that we only have 3 neurons in the hidden layer, and therefore our embedded vector has only 3 dimensions. The output layer of Word2vec neural network is softmax. Softmax is the outer layer for multi-class classification. We use the softmax to output the probability of the nearby words of the input. For example, the jumps over the fox. And the sum of all outputs of softmax is equal to 1. Right, also. So in our example, our 10,000 input 1/2 vector has been converted into 300 dimension word vector by our hidden layer, and then we can multiply the word vector with the softmax, and the softmax will output the probability of the word. So this is why the author choose the softmax in a model. Here's the formula of softmax function. First, we multiply the input word vector Wt by the weight vector of softmax function. Then we can calculate the score for all the words in our vocabulary. Right, so we can calculate scores for all the words. The higher the score means the higher the probability that the certain word is in the neighborhood of input word Wt. Then we can normalize the score to make sure the sum of all outputs probability is equal to 1. Right? So we iterate through all the words in the vocabulary and then calculate the normalized score. This is softmax function. So the score Wth computes compatibility of words, the input word Wt with the context, which means the other words, and we use dot product to calculate the score. Okay. Then we train the model by maximize its log likelihood. We calculate log likelihood of the softmax function, and then we try to maximize it. Another important trick for natural language processing is sampling important words. In other words, we need to remove non-informative words like the. Right? So if we put the in the training data, there will be a lot of noise. So usually we will remove the non-informative word like the. The authors of Word2vec have proposed a probability model for selecting the words. So Z of Wi is the occurrence rate of word Wi, and the P of Wi is the keeping probability. So basically, the more frequent of the word, the less probability that we will keep that word. The probability of keeping the word is around the square root of the occurrence rate divided by the occurrence rate. The probability output is shown here. So the less frequent of the word, the higher probability that we will keep that word. Another important technique introduced by the authors is negative sampling. The problem of training a Word2vec is that there are too many parameters to learn at training. It means that there are too many negative words because usually there are only a few words in your neighborhood, or there are only a few nearby words. So we don't need all other words as negative samples. We only need to select a few other words as negative samples. The negative samples means that the output probability is 0. The original paper select 5 to 20 words for small data sets and 2 to 5 negative samples words for large data sets. Remember, our goal is to maximize the log of softmax function, right? And the log of softmax function is equal to the score of WT context minus the log of other words. So the negative sampling can reduce the number of words in the second turns. Now let's see some interesting results of Word2vec. After training the skipgram model, one question is how to evaluate the performance of Word2vectors. Okay. The authors propose an interesting method. First, he shows that the distance of the man vector and the woman vector is equal to the distance between the king and the queen. The author claims that the vectors capture the meaning between the male and the female. Right? The vectors capture the distance between male and female. Another example is the verb tense. The distance between working and worked is the same as swimming and swam. The authors claim that is another evidence that the vectors can capture the meaning of verb tense. The third example is that if you put all the country vectors and search the nearest capital vector, the vectors can correctly, the embedded vectors can correctly find the capital for each country. So that means the nearest vector of Spain vector is Madrid, and the nearest capital vector of Italy vector is Rome. So the relationship between the country capital are correct. The most magical result of Word2vec is that you can do vector addition and subtraction and get meaningful results. Here are several examples. If we add the Russia vector with river vector, then the output is close to the Volga river vector. If we add Germany vector with the capital vector, then the output is close to Berlin. The most famous example is that king minus man plus woman is close to queen, which means we remove the main part of the king and add woman, then it means queen. So those examples can show that the Word2vec somehow captures some semantic idea of each word. That's why the Word2vec is so popular. Let's see how to use Word2vec in Keras. In Keras, this is called embedding. Keras provides an embedding layer which can import Word2vec parameters. In fact, it can import different kinds of embedding algorithm models. Okay, let's see what's the input parameters. First, we need to define the input dimension, the dimension of our one-hot encoding vectors. In other words, this is the number of words used in our vocabulary, the number of word indices. Second, we need to define the output dimension, the dimension of our embedding vectors. That's it. Just import embedding layer from Keras layers, then define the input dimension and output dimension. That's it. That's how we use embedding layer in Keras. Very convenient. Let's apply the embedding vector to classify IMDB dataset. Okay, so import IMDB dataset from Keras data and import a sequential model. For this dataset, we will use 10,000 words. So the max features is 10,000. And then we set the maximum length for each text to simplify this demo. The author, Chole, select only 20 words from each review. Remember, the target problem is to classify reviews into positive or negative. Okay, by selecting only 20 words, this make this model less accurate, but this code is only for demonstration. Okay, 20 words is not enough for a whole review. So we load the data from website, and then we do pre-processing, which need to pad sequence to cut the sequence to 20, and if the review is less than 20 words, then we pad zeros. So we use the pad sequence and set the maxima length. Then we create the sequential model as usual. Then we add the embedding layer into our model. So input dimension is 10,000 because we have 10,000 words in our vocabulary. Right now we select a very small embedding vector because we want to train an embedding vector, and the dimension is only 8. Okay, and the input data length is the maximum length, which is 20. Then we flatten the data, we flatten the tensor and use a dense layer, a single neuron to do classification. We use logistic regression, so it's a single neuron with sigmoid activation function. We compile it and use RMS prop to train the model, and we choose the binary cross entropy loss and use accuracy as the metric, and we can fit our model. However, the training results is terrible. We can see the validation accuracy is nearly unchanged, and the training accuracy quickly reached 100%, which means overfitting. So why is overfitting? Because there are actually a lot of parameters in the embedding vectors, and an embedding model need a lot of text data to reach a good accuracy. So it's not a good idea to train our embedding model on a small text data set like IMDB. So the best policy is to use a pre-trained embedding model. Let's try to use pre-trained embedding model to see if we can improve the model accuracy. Here we use the model called GLOVE, Global Vectors for Word Representation. This is not Word2vec model, but it's still very effective embedding model. It was developed by Stanford in 2014, and it's based on matrix factorization of word co-occurrence. Remember that matrix factorization is popular for recommender system. So you can download the pre-trained model from Stanford website, and the GLOVE made an assumption that the ratio of word-to-word co-occurrence, the ratio probability, encode some form of meaning. Here's an example. So the ratio of K word and the other words. K includes solid, gas, water, and fission. This is the conditional probability of we find word solid given ice. For example, so this probability is that the solid and ice has co-occurrence, and the probability ratio of those two words. So from this table, we can see that among the four words, the ice has higher probability, higher ratio with water and the solid, right? And the steam has higher ratio with gas, and water and the gas, And if we divide the conditional probability, divide the K given ice by K given steam, and we will see that the solid has highest value or highest score, which may mean that the ice remove the steam possibility means that ice is solid. So that's the assumption of GLOVE. To use the pre-trained word embedding vectors of growth, we need to first download the text file from Stanford's website. The file name usually is called growth dot the number of training words. It may be 6 billion, and the dimension of the embedding vector, which is 100D in our example. So it's a text file. Each line contains one embedding vectors. Okay, so we we read the whole file and split each line. The first data of the line is a word, the corresponding word of the vectors, and the rest data are the embedding vectors. So there are 101 data in each line. Okay, so we convert the values into NumPy array, so that's coefficient, and we create a key value pair index. We create a dictionary. Each word saves the corresponding coefficient. So the total number of lines is corresponding to the number of words used in the vocabulary, which is 400,000. So you can see that this dataset is much huger than our previous small model, and it has been trained by 6 billion words. So it is very effective and not overfitting. So we define the embedding dimension, which is 100, and then we create an embedding matrix to save the weights or the coefficient download from web. So the size of the embedding matrix is the max word, which is 400,000 by 100. And then we save the vectors into our new matrix one by one. That's how we load the pre-trained embedding model from text file to NumPy matrix. Once we have loaded the pre-trained embedding vectors, we create a neural network using the sequential model and the embedding layer as usual. Just set the right input and output dimension. Okay, the input is 400,000 and the output is 100. Then we use set weights to set the coefficient saved in the embedding matrix to our embedding layer. Okay, so after doing that, we also need to set the trainable to false because we just want to use pre-trained model. We don't want to change the parameters. So remember to set the trainable to false. Okay, so we compile the model and do model fit and save the pre-trained model, save the neural network parameters. So what's the result? The result with pre-trained IMDB embedding model is here. So as you can see, right now the training accuracy start from 0.5 and increase gradually. So looks like this prevent overfitting by using a pre-trained model. However, the validation accuracy has only improved slightly. But this is because this model is only for demonstration, and we cut all the reviews into 20 words. Also, we can expect that the accuracy is low. So as without the pre-trained model, you can easily see that the model is overfit. So usually we will use pre-trained model for the text data, no matter it's text classification or other applications. TensorFlow has provided a very useful tool to visualize embedding vectors. This is called projector. You can open an online version here, the projector.tensorflow.org. Here is an example that Google has provided a pre-trained Word2vec model. This one is called Word2vec 10K. Okay, so the 10K has 10,000 vocabularies, or 10,000 and 10,000 input dimension, and the embedded dimension is 200. You can use your mouse to rotate the point cloud, and when you move the cursor on the point, it will show the name of the point or the word of the point. You can also use the search function, which is at the right panel, and let's try to search king, and it will show all the nearest point in the original space. King, kings, queen, throne, all are the nearest points to king. And we can try to search queen. Queen will show Elizabeth, Anna, King, and Mary. Those are famous queen in the history. Okay, so you can also try to increase or decrease the number of neighbors. Let's try to search Taiwan. Taiwan. So the nearest point of Taiwan is unfortunately China and Hong Kong, PRC, Singapore, Thailand. Okay. So we can try to search Taipei, and we cannot find Taipei in this vocabulary because there are only 10,000 vocabularies. So there's no Taipei, but Word2vec provide a bigger model, Word2vec O. You can try it. That will include Taipei. Let's try to search learning, and the words that closely related to learning is teaching and knowledge. So from the projector, we can visualize and find that the embedding model, the Word2vec, indeed has encoded some semantic information in their vectors, right? So we can use the vector to search related word. Usually the related word will be embedded into a neighborhood, so we can search the word using the embedded vectors. Now I want to introduce one of my research, image hashtag recommendation, which recommends hashtags relevant to the image content. So we need to recognize what's inside an image and then use Word2vec to recommend related hashtags. What is hashtag? A hashtag is a word or a phrase that preceded by the hash symbol that categorizes the company text. So created by Twitter, and now the hashtag has support almost by all social networks. Here's the statistics of Instagram hashtag. The most common hashtag is love, and the other is the Instagirl photo of the day. This statistics is a little bit old, but the most popular hashtag didn't change over years, which is love. Image hashtag recommendation is very challenging due to the nature of hashtag. So there are several difficulties of predicting image hashtag. First, the hashtags are abstraction. The meaning is abstractive, like love, cute, or something else. And also there are a lot of abbreviations such like OOTD, outfit of the day, or outfit tonight, or outfit of the night, or OTN. And also most hashtags are used to describe emotion, like happy, sad, or blue. And obscurity, some will take their photos as motivation, laugh out loud, or there are some new creations. There are new creations every day, and some hashtags are not relevant to the content, like the no filter or throwback Thursday, which means old photos, and some are related to the location, like NYC, London. So those difficulties make predicting image hashtag very difficult. How can we recognize new class that are not in our training dataset? Is it possible? Yes, we can use a method called zero-shot learning. Zero-shot is to identify objects that you have never seen before. The formal definition says that we need to classify test classes Z with zero labeled data. So that's why it's called zero shot. So the new data Z in test set, which we have never seen in our trained data set. So the intersection is 0. This is zero-shot learning. We do not have the training data for the Z classes. How can we train model to recognize new images that are not in our dataset? In fact, we need to leverage the semantic features. This is called attributes. We will like to leverage the words. We can use words to describe objects, right? So we can train our model to recognize the semantic features. For example, if in our data set we have horse and the stripes, then if we can combine the horse with stripes, and it should be a zebra, right? So we can try the feature and the feature classifiers to extract features, then do embedding. We need to convert the image features into a new vector space. On the other hand, we need to convert labels or the words into another vector space, and those two spaces are close related to each other. So if we have seen a zebra, which is not in our training data set, but we have extracted the horse feature and the stripes feature. We have learned the horse and the stripe feature before, so we know so our model will embed the zebra to a new point. The new point is close to horse and maybe stripes, but it's not exactly the horse. And we hope this point is close related to the word zebra. So by using these semantic features, we can convert. Of course, we need to have extra layers to convert our image features into semantic features. So let's call attributes, and then we will search in our new semantic feature space and find the right answer to our new class. Google has proposed a zero-shot learning model, which is called DeVice, Deep Visual Semantic Embedding. It's actually combined the ImageNet feature and the word embedding features. So there are two parts of this model. First, we need to have image classifiers, which is pre-trained on ImageNet, so it will extract the features. But we will remove the softmax layer. Remember, in previous class, we have introduced how to reuse the features. We need to remove the top softmax layers, and the output are the features. Then we need to learn the embedding. Here is called transformation. The embedding will embed these features into semantic space. So what is the semantic vector space? Actually, it's the semantic vector space was trained using the Word2vec model. So we will embed each word label into the Word2vec space, and then we will learn the transformation to convert the image features into the embedding space. And this is called the Deep Visual Semantic Embedding Model. The semantic comes from the Word2vec, which was trained by Wikipedia data. So there are a lot of semantic information in the Word2vec, and the image features are pre-trained on ImageNet. So by learning a transformation, we can transform image features into a Word2vec. So although we have never seen zebra in our training data, then we can use the transformation to project zebra into the right Word2vec and find the right answer. For example, I'm not sure if there is a zebra class in ImageNet, but here's an example. So we can do a transformation. So the device, the author select 200 labels from maybe ImageNet and use it to recognize a total of 1,000 labels. And the device can successfully reach 9% accuracy on recognize around 800 unseen class in the training data set. So you can use 200 to train, and then successfully, we should not say 10% is successful, but have at least highest accuracy on a large scale on same data set, higher than other models. This is device deep visual semantic embedding. Back to the image hashtag recommendation. The most important paper in this field is the paper published by Facebook. Not surprisingly, because Facebook owns Instagram, right? So the paper is called the User Conditional Hashtag Prediction for Images, published in 2015. So the first model, they proposed the three models. The first model is the traditional zero-shot model. So they try to do a bilinear embedding model. They use the feature pre-trained on ImageNet, as well as the I guess they have trained on Instagram images, and then they train a hashtag a Word2vec model for hashtags. We can call it hashtag 2 vector, right? So they have an embedding vector for hashtags. They embedded the hashtags into the semantic space, right? So which means the hashtag with same meaning will be close to each other, and I will also use convolution layer to embed it into feature space. Okay, and then they calculate. They learn the conversion. They learn the transformation to transform the image feature into semantic space. This is the first model. The second model adds the user bias or user information. This is because usually the user has its own preference of hashtags, right? So user will tend to use the same hashtags. So it will be useful to add the user information, user profile. So they concatenate the user profile matrix with the image features, and then transform it into the embedded semantic space. It's called the user bias model by the authors. The third model is use the outer product. It's a common technique to multiply the image with the user vector. That will create a very huge matrix, it's an image, number of images times the number of users. So for this huge matrix, that we will do a low rank decomposition. We will use a low rank technique to approximate the matrix. So we have a new matrix beta, and the matrix beta encodes the user's preference for each image, and then we project it into the embedded semantic space. So there are three models: bilinear embedding models, which is the traditional zero-shot model, and the second one is the user bias model, which concatenates the user profile with image features, and the third is the user multiplicative model, which make a outer product of image feature, image descriptor, and the user metadata, and create a large matrix and use low rank to approximate it, then project the new matrix beta into embedded space. Here are the user profile and information used in this experiment. So Facebook extract the metadata include age, gender, and the user's home city as well as the countries. So those informations are helpful for recommend hashtags. Here's the experiment results. Facebook used 20 million images and 4.6 million hashtags. They are average 2.7 texts per image. Also, they have normalized, make the training data more balanced. We know that hashtag is a long tail problem, or that most texts are used on popular text like love, cute, or something else. But there are many other hashtags with less training images. So we need to make our dataset balance by cut some training samples, cut the training samples of the popular hashtags. So here's the results. The D means the dimension of the embedding vectors. So Facebook tried to train the H2 vector model. Let's call it H2 vector model, which embed hashtag into semantic space. So the choice are from 64 to 512. But in our experience, they use the precision at 1, the top recommendation, and the recall at 10, and accuracy at 10. First is the result of bilinear model. In bilinear model, we can see that the smaller dimension of H2 tag vector produce better results. So it means that large dimension is not necessarily better. The second model, user biased, shows similar results, that smaller embedded space has better result. Okay, and finally there are three-way multiplication model. Okay, because 64 generate better results, so they fix the embedding H2 tag dimension to 64 and try different low rank approximation of their image user outer product matrix. Right, so you can use 50 dimension matrix to approximate the image user matrix, right, from 50 to 400. And we can show, we can see that by ending user profile, both precision and recall and accuracy has increased, right? That's very straightforward, because user preference is very important in recommending image hashtag, right? So then either a concatenate of user image vector or the outer product will generate similar results. Okay. Word2vec was very successful in natural language processing and went beyond the NLP field. Now it's a very popular unsupervised dimensionality reduction method, and there are many real-world applications. I just add a few examples here. So Airbnb, they can embed the image of their apartment and also the text description together and then make an embedding vector. Also, they create an embedding vector of all their items, apartment items. So if the user is interested in one type of apartment, they can use the embedded vector to search in other objects. Another example is that Yahoo has embedded the user's email and then can do the email search. Spotify has embedded the music genre, music and description, maybe some audio data together, and they can create a recommender system. So we can see that recommender system use Word2vec a lot. That's because the Word2vec model can preserve the semantic meanings of their items. Another example is that Google uses Word2vec to search users' log. There are just a few examples, but I believe almost all software companies have used more or less some Word2vec in their machine learning systems. That's it. That's my introduction to Word2vec. I hope you enjoy it and can use Word2vec in your future projects. If you want further information, you can read the original paper written by the Mikolov Thomas and the other document that has explained Word2vec. Also, the blog that provide many useful pictures in my slide. Thank you.